when you want the next slide up.
Okay, thanks. Thanks, Tim and the SBAG committee for letting me give a presentation, and that sort of qualifies for the now for something completely different category. But I think this will be of interest to the SBAG community broadly. I want to talk to you about a new initiative, a new institute that we've formed at ASU in collaboration with Lockheed, with a spinoff of Lockheed called Geoshare, and also in collaboration with colleagues at the University of Arizona and NAU. As many of you in this audience know, there are many, many more missions proposed and conceived of than NASA or other space agencies around the world can actually fund. Something like 10 to 15 missions proposed for every one that actually gets to go. And of course, most of those are great missions. Many of us have written proposals for those great missions that didn't get accepted and all that. So there's clearly a lot of science that can be done that's not being done because of resource limitations globally in the global space exploration world. And so at ASU, we've decided to try to team with a couple of other space-savvy commercial partners and university partners, and try to test a new model to enable more deep space missions to happen. So not trying to compete with NASA or ESA, JAXA, et cetera, but trying to basically augment what they can do, realizing that so much more can be done than is being done. So we've created a spin-off of the ASU research arm, a nonprofit organization called the MILO Space Science Institute. I want to tell you all about that. So next slide, please. Great. So our goal is to try to make deep space missions affordable and accessible to universities and space agencies around the world. And many of you also know that just in the past few years, the past 5 years, 10 years, we've seen this proliferation of space agencies. There's something like 60 space agencies from countries around the world now. Many of them, of course, very, very small, many of them with extremely limited budgets and extremely limited experience, and of course many of them not able to get in on the sort of big missions that are done by the traditional NASA's, ESA's, et cetera, because they either can't afford it, they can't afford to run a big mission like that, or they just don't have the heritage and the experience to be able to compete with other potential players out there that provide instrumentation or mission services, what have you. So we're trying to address that need. Next slide, please. So I mentioned it's a nonprofit. We collaborate with Lockheed, which of course has an enormous amount of experience in mission design, spacecraft fabrication, testing, operations, et cetera. And Geoshare, which is a spin-off of Lockheed that some of you may not have heard of. It's their job is basically they organize these series of Earth orbital satellites that they used to be called condosats. Get a bunch of individual institutions or companies that have equipment, experiments that want to go to the same place in Earth orbit, low Earth orbit, or GEO, and they all band together, form a consortium, and each member of the consortium pays a fraction of the total cost of the spacecraft plus launch, but they get to go where they need their equipment or their experiment to go, and they negotiate basically the resource split among themselves. And this is Geoshare is a spin-off from Lockheed that organizes that consortium, and Lockheed does a lot of the integration work associated with that. So I have a colleague who's the CEO of Geoshare, and we were talking one day, and it's like, would that model work in deep space? And we both shook our heads and said, who knows? But that's basically what we're trying to test, whether we can build a consortium-based model of member institutions to run a deep space mission. Next slide, please. So the idea is to pull a series of members together like Geoshare is doing in Earth orbit. Each of the members may contribute an individual spacecraft. I'll talk more about this in a moment. They may contribute instrumentation. They may just want to get their particular scientists or students or industry members involved in data analysis and technology development, et cetera. So a variety of reasons why members would want to join an organization like this, and I'll come back to that. We're also offering for members of this, this consortium that we pulled together a small sat accelerator program. So this would be funding and technical resources given the experience from Lockheed on spacecraft, instrumentation, engineering, given the experience from ASU on science, analysis, operations, instrumentation development, education. So the idea is that players who want to be part of this, members who want to be part of this who don't have the experience, can get that experience built up by being part of this consortium. Next slide. So some member organizations, and we've been in conversations and reaching agreements with a number of them, and I'll show you a slide in a moment. Some are just out there to try to mature technologies and their individual space science programs. Countries or universities that have never flown a deep space mission, that want to do TRL development, maturation, they want to test a new sensor or a new instrument suite or an entire spacecraft. These are universities, government agencies, industries. How do they get that experience? They can, launch a CubeSat into low Earth orbit. Those are frequent opportunities. They might get an opportunity to do something like Geoshare does in Earth orbit with a higher fidelity satellite. But the deep space opportunities are extremely rare and hard for organizations to become part of. So by becoming a member, which just requires buying your way in to this member-based organization, by becoming a member, you get access to the ability to mature technologies in deep space. It's also designed so that most of the membership fee to join goes back to the individual members so they can create their own intellectual capital, their own workforce. If a particular country has never had a deep space satellite and they want to have their first one, they join our organization. They pay a small fraction of what they would have paid for a launch because we have 20 plus or minus 10 entities all banding together in this consortium, and they can get their equipment out into deep space. The small sat accelerator program helps that, and they can demonstrate operational capability as well. So there are a number of countries out there and companies that really would like to be competing on a level playing field for opportunities that NASA enables for instrumentation or involvement in large class missions, or ESA or JAXA, et cetera. And this is a way for them to get that heritage and technology maturation and build their own workforce up in a way without having to initially compete, but that can make them then competitive. Next slide, please. So, why would an organization, a country, a university join? Okay, you get access to the small sat accelerator, you get access to deep space missions at a fraction of the cost it would cost you to do it alone. You get the experience of the sort of NASA and ESA way to organize, to develop, to design a mission, to go through the standard PDRs and CDRs and tough review process with oversight from organizations like Lockheed and others who have a lot of experience. You get to build, test, qualify hardware. Integration is provided by Lockheed, so we wanted to make sure that members have some assurance that what they're going to participate in, what they're going to pay for, is going to work. And many of you know about the history of small sats and CubeSats, and many of them are low cost, and many of them don't work. And for many of them, the goal really isn't to try to do science; it's to try to educate students and develop workforce and provide opportunities like that. What we're going after is science focused. And so that's what compelled us to bring in a quality organization with a lot of experience like Lockheed. And as you'll see, I'll talk about our inaugural mission. That's why it's not a $100,000 mission. It's a hundreds of millions of dollars kind of mission, because we really want it to work and do top quality science. We've got other advantages. technology development. We have an academic and education council, and here's where we have representatives from the small body community at ASU, UA, and NAU who are involved in helping to define this first mission. Next slide, please. Yeah, so we had to pick an inaugural mission to try to see if we could demonstrate this concept, and we picked. We had to choose the constraints that were driving us. We wanted to do something relatively quick, so we had to be fairly close to home. Relatively inexpensive, so not like Discovery or New Frontiers class budgets, but also not Tinker Toy kind of budgets. So relatively affordable, assuming we get a decent number of members to join in. And then we really want to do decadal quality science. We want to try to check off some boxes in the decadal survey, and that's what drove us towards this idea of a Geoshare, which is a single launch mission that carries 6 or more small sats or CubeSats, each of which is doing a flyby of a near-Earth object that's relatively close to the Earth. And you guys know these numbers better than I do. Lots of near-Earth objects out there. Lots of them are on the potentially hazardous asteroid list, but only a very small number of them have been looked at up close. So with one mission, say with 6 small sats or CubeSats that are doing flybys, some of which could fly by multiple objects, with the propulsion capabilities that are available now in small sats and CubeSats, we could easily double the number of near-Earth objects that have been visited by spacecraft up close. Of course, getting up close means you get geology, means you get shape, means you get composition in great detail. If you're carrying standard kinds of straightforward instrumentation, cameras, spectrometers, maybe if we can get close enough and the object's large enough, we can even get mass and density. So really, in one mission, the idea is to ramp it up and get a lot of them looked at very closely, and do the kind of science that's going to appear in Science and Nature, like we just saw for the Dawn mission. Next slide, please. So that's our inaugural idea. Here's just a cartoon graphic, a single launch that we're planning for 23 in a relatively modest-sized launch vehicle. It could be a SpaceX, a Blue Origin, or something of that class. Launching multiple satellites off of kind of an Esper ring kind of architecture, each of which does a close flyby. When we did an analysis of the number of objects that we could fly by close to for a launch in early 23, given the known population of NEOs now, we come up with about 100 objects, about 100 asteroids, and about 20 near-Earth comets. So there's a rich number of objects out there. We could go for spectroscopic diversity, we could go for size diversity, binarity, etc. You all know what the diversity is out there, and that would be partly the job of the Science Council to help decide on the final number of objects encountered. Next slide, please. So we rolled this out at the IAC in Bremen last year. An enormous amount of international interest. The organizations at the top have signed expressions of support, and we're in negotiations with them now about membership opportunities, and the organizations at the bottom are highly engaged. We're giving presentations, we're having telecons, we're doing a lot of back and forth about their potential levels of interest and involvement. So this was a surprise to me. I really did not know if we would get a lot of interest out there, because people you have to pay money to join, and once you join, then it's a negotiation among the consortium that's developed, kind of like they're doing in Earth orbit, to figure out how to actually lift this mission. Next slide, please. So that's kind of the high-level summary. Just a couple of other things to hit. We're using kind of a Hubble-like model for data rights. The idea would be institute members have access to the data in a sort of proprietary 1-year period like Hubble has. And after that point, our intention would be to make the data public. Of course, if people have, organizations have data having to do with their particular instrument or technology maturation that's competition sensitive, they can, obviously, we would negotiate their own release timescale for that. The initial mission, we estimate that it's going to cost between $200 and $250 million, so it's not chump change. There are different buy-in levels that we're pitching to those organizations that you saw. Maybe they just want their scientists to have access to the data. That's maybe $1 million. Maybe they want to build an instrument. That's $5 million. Maybe they want to build an entire spacecraft. That maybe is $20 million. We're working out all those numbers. And like I said, most of that money goes back to the institutions sort of paying their dues coming in. Everybody has to chip in to buy the launch vehicle. Everybody has to chip in to help pay for the integration. But then if you want to build the spacecraft or the instrument or process the data at your own home institution, you're going to get that funding back. So it's a test of a model. It's kind of like ESA in many ways. ESA has many member nations, and they all pay into the organization, and then they get a bunch back, and the workload is spread out among them in equitable and politically acceptable ways. And we would imagine having similar kinds of issues. We don't know if this is going to work. It's entrepreneurial. We've set ourselves up some relatively near-term gates to see if we can get through this. But it's also it's a potential way to help fill in the gap of between the number of great missions and great science we could be doing and the number that are actually conducted around the world. Thank you.
Thank you. Time for a couple of questions.
Online. Okay, what is the expected delta V for the small sats? Online question.
It's relatively small. Because we have so many objects to choose from, we have the luxury of being able to use the launch vehicle itself to get us in generally the right direction, and then a few hundreds of meters a second to a few kilometers per second delta V, which is within the realm of possibility of current and soon to be online propulsion systems for small class spacecraft.
Okay, we have one more question from online. It's very interested to hear that the UKSA is in this conversation. Who are they talking to there?
I can't remember the names, but we have been we took meetings with the leadership of UKSA, and we'll be giving a presentation next month there'll be a meeting of the UK small bodies community at the Royal Society in London, and we'll be giving a presentation about this there, gauging interest. But ASU has a collaboration with some members, some universities in the UK, and so we've been talking directly with some university researchers as well.
Okay, one more question.
Hi, Jim. Andy Ripken at APL. I'm already sold, of course, on the diversity of the NEO population and how we need to look at more objects. And I have a personal take, but I think this is an objective comment. I guess I would just caution you not to oversell what could be done, because in the past decade or so, people have gone in and convinced themselves, for instance, that there could be a ton of accessible asteroids that could be mined, or there's going to be a lot of asteroids that humans could get to, and it turned out to be much more difficult than originally thought. And I agree that there could be a lot of asteroids that could be flown by, but to fly by them with the kind of instrumentation to get the kind of science you talk out of it on a very small platform could be really challenging. So I think, again, I would just caution you not to oversell what can be done, because if you oversell it and then people are disappointed, that would really be bad for the community as a whole.
Yeah, that's a question, Andy. That's a great point, and I completely resonate with it. Our goal, this is a demonstration of concept, and our goal is to keep it as simple as possible. So simple imaging systems, simple near-IR point spectrometer, try to get close to objects larger than a few kilometers, and try to get a mass from delta V of the comm signal. No really new technology development, pretty straightforward. The assumption is that some of these objects will be a lot more interesting and curious than we're probably imagining, especially some of the spectral classes that we've never seen up close. And so hard to predict what we'll get out of it. But it's a good point. And remember, some of the members don't really care about the science. They're doing it for technology development, engineering development, or even just educational workforce development. and we'll certainly be able to get those aspects out easily. But it's a great point.
Okay, thank you, Jim. Okay, so next up, and a reminder again that Rick Benzel will be talking at 1:30 instead of